Good afternoon, everyone. We'll continue with the next section, which is computer system architecture. So last week we talked about the computer system organization. So basically this is about one computer system. It's organization. For example, it's a CPU, it's memory, it's I/O devices, it's a hard disk, like this one. And then we want to talk about the computer system architecture. Here means we combine several computing systems together. We got one system. So this system may contain several computer systems. So this is the difference. So we talk about this is architecture. That means how different computers will be connected with each other. Okay. So we have two types of architectures. First one, of course, is just a single general purpose processor. That means this system is only one computer system. Okay, one computer. So that means it's maybe it's one computer have one CPU, several CPU, multiple cores, but most probably maybe only one CPU and then one core. But you may have one CPU, multiple cores, or several CPUs, several cores. So it doesn't matter, but it's only one coherent system. That means one operating system, one set of hardware, one I/O set of I/O devices, and so on. So this one, in the past, we use this one for special purpose. For example, if you use this one for the industrial control, we control the robot movement, we control some automatic operation, and sometimes maybe even in our one computer system, we may have some special smaller systems just control the storage transfer, the data transfer. Like these ones, we said this is a special purpose processor. Okay, single processor system. And then the more popular ones in the current stage, we have the multiprocessors. So for this multiprocessor, that means you have multiple sets of processors. So the first question is that why we want to have multiple processors connected to each other. Just consider, for example, you want to develop a very robust system. If you only have one set of computing system, if it has something happened due to hardware failure or just even the power supply issue, right? Or anything, just like software or hardware failures, this is very possible. So for faults, software, hardware faults or failures, so it will be very possible happen. And then if for this one is very high requirement, that means high ranking on the robustness. That means it's not like our personal computer. If it's something wrong, we can restart. But for example, if this is some system which control the power grid of our local metropolitan area, correct? Like the scheduling of the power. Okay, so that means this is very important. So we want to make sure even one computer is down, we have some backup computer which can continue the tasks. So if like this, we need to use multiprocessors. So it's a system. That means we can use several backup computers. Okay. So for this one, this is one purpose. So for robustness, sometimes maybe also we want to do parallel programming. Just consider, for example, if one computer can do the task, no problem. But if the task is very complicated, or in terms of complicated, maybe it's a large amount of data need to be processed. Maybe the processing, the mathematical calculation or the data processing, information processing is very complicated. Like we mentioned, we have task parallelization, we have data parallelization. So data parallelization means you have a lot of data to process, like big data. And the task parallelization means you have a very complicated job. This job consists of a set of tasks, several steps. So it may be more complicated. And then some tasks can be paralleled. So this is task parallelization. So either task parallelization or data parallelization, we want to finish this task, this job, on one computer system. That's easy for us to handle. Okay? We don't want to run some part of the job on one computer and then another part of the job on another computer, and then finally get the results combined on another computer. So if it involves manual operation, that will be slow. So either instead of using manual combination, we can use a computer system. So that means we use a cluster. We put all the computers combined together, and then we schedule the task on the cluster based on the load. For example, which computer node, cluster node is available, and then we can assign some job to it. And then maybe there's a master node which can master the scheduling of the whole task, okay, whole job, and then distribute the tasks among the slave nodes. And after finish, we combine the results together and then get the result on the master node, then return the result to you via the master node. So this is basically the idea. Just like we want to utilize multiple computing nodes or CPU cores together, because multiple resources combined together will be more powerful. Right? So this is the reason we want to have multiprocessor systems as well. So that means robustness and better performance. Sometimes we call the through output. Right? So this is the reason. So sometimes we also call this one is a parallel system. So if you have interest in learning parallel programming, then this will be very important part. And then we also call it the tightly coupled system. Tightly coupled, that means they share some resources together. If it's loosely coupled, that means each one is individually working by itself. They can work by itself. If it's tightly, that means they share some information. They make content for some resources. Okay. So for this one, the advantage is very easy. We mentioned because we have multiple processors combined together. Each one maybe is not so powerful, but if we have many processors, we put them together, and then we can finish a task very quickly, because we can divide the job into multiple small jobs, and each one is running a simple job. Each one can finish early, and then combine together, we can finish the result earlier. Three output means from the time the task or the job is submitted till the task has been finished. That's called three output of the job. That means what's the time range in between, from in to out. That's called throughput. Okay, throughput. And then increase the throughput of a system means within a unit of time, how many jobs you can finish. This is called throughput. Okay. So that means, for example, within 1 unit of time, I can finish 100. So I can finish 2. Okay, like this. That means how many jobs you can finish. This is called throughput. So we don't care about the complexity of the jobs, individual jobs. And the next one is the economy of scale. Okay. And then for this one, they don't need to, for example, they only print something occasionally. They don't print a lot. And also they don't need to store a lot of data in their local system. They can also share the power system, correct? So that means we can share all of these things, because this one will reduce the cost. So each one, maybe you have a CPU core, you have a CPU processors, but they can share the storage, hard disk. Okay, we have a hard disk they can share together. So all the data are saved in the hard disk. And the power system, we just use don't need to have multiple. Okay? You can use switches, so combine, just connect all the computers. And also increase the reliability we mentioned. In case of there's a failure or there's a fault, and then we can do recover quickly, right? Just catch up. We don't need to stop. And here we want to talk about, we have two types of these multiprocessor systems. The first one is asymmetric multiprocessing. So if we set it as asymmetric, that means each one will do differently, correct? That means asymmetric. If it's symmetric, it means each one behaves similarly, correct? Same. So that means this is the difference. Okay, if it's asymmetric, each processor is assigned a specific. Okay, this is the arrow. A specific task. Okay, I will upload the updated slides, because I also did some changes. Okay, so for this one, just like each one will do some specific tasks, which is specific means different from others. Okay, so that means it's not consistent or uniform. And symmetric means they can do all the tasks. So that means just they can do everything. We don't allocate, okay, you do something which is different from others. So each processor can do the same type of works. That means they can do the same range of works. So each work can be scheduled to each processor, so they have the same functionality. We don't assign a specific functionality to each computer processor, each processor. So let's look at this one. This one is a symmetric multiprocessing architecture. So in fact, here we have two processors. Okay, we have two processors. Look at this one. And then each one you can find, so is CPU 0 is one processor, and then CPU 0 and CPU 1 another one. Each processor has its own registers and cache, but they share the main memory. This is only one example, okay? You may have different ones. So this is just show you, maybe your computer have multiple processors. For here we have two processors. We put these two processors inserted on the motherboard, and each processor itself has its own register and cache. The reason is that we want to use register and cache to process data quickly, correct? So we don't want to share, but sometimes we can still be able to share. Later I'll give you one example. Okay, so this is like this one. Okay, just one example. But they don't need to have its own main memory. The whole system has several, for example, several pieces of memories, and then inserted. They can share as long as they have some available memory. They can save their data there, and also they can share the data via this method. For example, they process the same data belonging to the same process, same task, same job. Okay, so this is the symmetric. Symmetric for here, that means each CPU processor is general to process any task. They don't have specific definition for some type of tasks. Okay, and then let's look at, maybe you heard a lot about another one called a dual core. For dual core. So for dual core, this means we only have one CPU, but it has two cores. They share some information, but they also have their own hardware. Okay, they share some hardware, but also they have their own, like this one. Right? For example, this processor, only one CPU processor, but it contains two cores. Each CPU core means it's individually computing unit. Because this one is available to compute. Okay? They can run a task. They can run. Later we talk about this one should be renamed to be process. Because task unit is a static concept, but process means it's running. So it's a task running with its resources available. Okay, so that means it's available to run a process or a thread. Okay, so this is another one which also can run a thread, or thread is the lightest running unit. Okay, so process is the smallest scheduling unit. That means the schedule we must use the process to schedule. You cannot schedule a thread as a unit. So thread is within the process. So like this. Task maybe have several processes. Each process maybe have multiple threads. Okay. Tasks. And then you have process. For example, you are using a prayer line programming, okay? And then you have multiple threads. Okay, just for example, we just give example. So process is the scheduling unit. Schedule. This one is running unit. So running unit, that means we can run here. Okay? Scheduling, that means we can schedule this on this CPU. So this CPU can run this process or run that process, but you cannot run some part for this one, some part for another process. So this is the different levels. You can run multiple threads. For example, this one you can run two threads. Okay? Two threads within this same CPU. So for the same process, run same two threads on this one. If it's not enough, maybe you need to get another process. For example, you have four threads. You need to allocate two CPUs for dual core. Okay, this is just like you can find they use the register. They have their own register. We know, for example, if we do C equal to A plus B, we must load the data from memory to register, and the memory to register, and then we use arithmetic calculator is hardware. We do perform the arithmetic operation and then save the result into another register. So register is quickest resources here. So it's quicker than cache, but more expensive. So that means we cannot have a lot of register. So that's why we have different levels of storage. So for here it has its own register for quick list, quick operation. And then we use L1 cache for this CPU core 0. And then we have another L1 cache for this one. So the cache, so here we use level 1, level 2 cache. If the speed between register and the main memory is very different, so that means there's a lot of difference. For this one is 1, this one is 100. So we may need to insert two levels cache to smooth the speed difference. For example, first one in elevate from 1 to 50, and second one from 50 to 100. So that means cache temporary state data store the data, correct? Store the data, and also they can bridge the difference in the speed. But you can find here two processor CPU cores within the same processor share this L2 cache, because this L2 cache maybe is larger. This one you don't process a lot of data, but you may need to preload the data from main memory to the CPU system, correct? For the CPU processor system, for this processor 0. So that means this one should be larger. After you finish, and then you temporarily save some data, maybe you need to perform a lot of operations, and then you get some data done, and then save back to here, and then just consume next piece of data, continue. So this pool is larger, this pool is smaller, okay? So that's meet our requirements, okay? So for the two CPU cores, they can share some caches, they can have their own caches as well. That means they can share some hardware, but they also have their own specific hardware, okay? So this is another very traditional example for multiprocessor system. Just multiprocessor, you have multiple processors, but here we talk about within one processor you have multiple cores, okay? So the multi-chip or multi-core. This is like a computing unit, okay? Computing unit. So for this one, system containing all chips, that means we put all of this down in one system, and then chassis containing multiple separate systems. So within the same motherboard, you can arrange multiple processors. In each processor have multiple cores. Okay, that will be quicker, correct? Rather than just using different chassis. Chassis will, because there's a distance, different systems, that will delay the speed. Okay, this is an example. Let's look at further computer system example. I believe if you open your box kind of your PC, you will see these things. So let's look at, for example, we look at the CPU here first. There's a processor socket which can insert the processor. That means it has its own register and cache here as well. And then we have DRAM slots. So DRAM slots, this will be for memory, and PCI bus slot. So for some other devices like a monitor related, like a display. For example, we want to use GPU, and then you need to have maybe two rows PCI 32, maybe 32 pins. And then for here you can find we have a lot of things for I/O devices, maybe HDMI, maybe VGA, maybe some monitor, and USB, and voice, audio, video, input, output, and also maybe network and power system as well. So that means all of these things is related to I/O devices or power system, okay? And this is the expanded for memory. Of course, you need to have some memory, but you can expand. So for expansion, okay. And we didn't mention about that. Maybe we have a disk, okay? We have hard disk. We are attached to here as well. Use some interface. Okay, this is a simple example to show you the computer system. Okay. So next one we want to talk about. So the previous one we said is multiprocessor, single purpose, general purpose system, single processor, and then we have multiprocessor. Here we talk about cluster system. Cluster system, that means we combine several individual computer systems together, fuse them together, get a larger system. So it's like a network of computer systems. Okay. So this is like multiprocessor system, but multiple systems working together. So the most important thing that if each individual system can be just different, they don't need to be homogeneous. That means they can be on within different operating system. For example, my computer system is Linux, your computer system is Windows, and another person is iOS, is Mac, and then we can combine them together to get a cloud computer system or distributed computer system. So it's a cluster system, right? So usually for this type of system, we need to use sharing storage. So it's very possible because maybe you need to process a lot of data. So rather than just each computer system has its own storage system, so that's not good for data sharing as well, data communication. So we can have a storage area network. So that means we combine several devices together, fuse them as a SAM. We'll explain this one in the next slide. Okay, the storage area network. So this one will help a lot in the improvement in the cluster systems. So next one, so we talk about the multiprocessor system. It has some advantages, okay? So what's the advantage for here? Okay, so similarly like the previous, for example, if we have asymmetric clustering, so this one we can have like a backup system. We call it hot standby. If one computer system is down, another one still be reliable, okay, to take the task, to take the job. So that means will not hurt, will not stop the running. So this is the asymmetric. So asymmetric, that means one or some may be running and others just ready to be run. So we call it asymmetric. Okay, and then we also have a symmetric clustering. So similarly, you can understand. Okay, if we want to use a symmetric clustering, each one can do general tasks. The most reason is that we want to improve efficiency, right? Improve efficiency. So that's why we have the high performance computing. So we combine multiple computer systems together to fuse together to get a cluster system. The reason we want to get a high performance computing. Basically, high performance computing just want to complete some complicated tasks in short time, right? So basically for this type of things, we are using parallelization. So parallelization, the idea we mentioned before, maybe for several times. So the basic idea is that a task is complicated. We divide the task into several small tasks, and then we run each small task on one computer system. After each cluster node has finished its job, we combine the results together to get the final result. So this is the parallelization. Okay. For example, like some parallel clusters may have used distributed log manager. Why we want to use the distributed log manager? Because you can find that they share some resources. So how to make sure they don't have conflicting access? For example, I want to write, you also want to write. So we need to have some access control. So that's why they have a distributed log manager. The log, that means if for exclusive operations, we do not allow them to run at the same time. If it's non-exclusive, like a read, okay, everybody can read. But if it's exclusive, write and write, read and write, and write and read, like these things, we cannot allow them to do the same time. Okay? We can only allow one write at one time, exclusive others for others. And once the write is done, we allow another one to test. So lock and unlock. Once the write is done, and then you can unlock the resources. So in fact, for the process control for the second module of this book, this course, we talk about a lot about this one, how to use the resources in a synchronous way and do not have any bad effect. For example, the data is bad because the data is false, it's wrong. So also maybe for deadlock, like these things. Okay, so this is the reason. Basically, for cluster system, the reason most important is that we want to improve storage, computational power, have parallel programming, and to improve the performance for jobs running, to achieve high HPC, high performance computing. And here we talk about the SAN we mentioned here, cat. So thanks to this SAN, so class systems has a lot of improvement in recently. Okay, so this is about the SAN. The basic idea is that we use computers interconnect each other. They share the storage area network. That means you may put a lot of different disks together, connected together. We use racks, cat, and then we connect them together, and then we can access these shared resources, shared disk. Okay, of course you need to have some file system. If you learn for example, like we have distributed computing framework. If you ever heard before, like the big data, so we use the MapReduce. We have a distributed file system. That means how to access the data, and then Hadoop, HAD. In our book, we also mention this thing. So MapReduce, if you have learned the algorithm, this one is exactly the idea is divide and conquer. The same idea. So if a task is very difficult to do, you will divide the task into small tasks, right? And then run on each computer. After finish, you just need to only submit its results to a control, maybe a master node. Of course, not here, right? Another one. And send the results. Maybe the data is already available on each computer, so you don't need to transmit the data from here and there. So you just locally process the data and then combine the results together. Just a simple example, I want to get how many students or how many credit hours have in total for this 4 semester. So we can count each class, right? How many credit hours, and then we have 2 campuses, and then each campus has many classes. Okay, each class is count itself, and then after that get a number, and then send this number to a master node. So then combine the results together, divide and conquer. So divide the task into small tasks, and then conquer each small problems, and then combine the results together. So MapReduce is exactly the same idea. So I have a mapper, jobs distribution, right? Distributed jobs among multiple computer nodes in this distributed system, computing system. Reduce means reducer. Combine the results together. You don't need to get raw data. You just need to count how many credit hours for each class and then combine. So that's the idea. And then MapReduce was proposed by Google. This framework, but it's not shared with others. So Hadoop is open source computing, distributed computing framework, and then it's implemented in Java. Initially, this one MapReduce was implemented in C++. So that means not easy, right? So Hadoop to meet the requirement for web programming, and then they just use Java re-implement this idea. So they have their own file system. For example, they have Hadoop distributed file system. They can access, of course this one you think is here, but in fact we have a lot of locations. They can find the location while we store their data. So they have a Hadoop distributed file system. So in our computer we have our file system, but not distributed. So in a distributed computing system, of course, we need to have a distributed file system. Okay. So that means for this storage area network is similar like this. It also has its own file systems. You need a distributed file system. You cannot put all the things together. They have combined together to form a network, not physically in the same location. This is not safe. We need to have backup replicates. We may need to distribute the replicate in a lot of locations. For example, if USA, we may need to put something in Washington, something in DC, something in New York, someone maybe in Florida, Texas, maybe Mississippi, any location, maybe Arizona. Some if they have some data center there. In case we have some disasters, for example, along the beach, along the Gulf Coast, we may have hurricanes. Maybe in California now we may have fires. And in case, we just want to make sure we can still have the data if some has something wrong, hardware failure or natural disasters. Okay, anyway, this is just like extension. Why we need to learn these things? So in fact, this is still low level things. Okay, when you learn this Hadoop distributed file system, it's still like learning operating system, because if you have known this one, when you code for this distributed system, you are just code for one computer, because they will hide the differences there. You don't need to care about where it's located, and then you just need to follow this framework. So you can find out, we always use this method. Hide the physical differences, we have operating system, and hide the system differences, we have a network operating system, and hide the differences of different computers, networks, and so on, we have this distributed computer network framework, Hadoop, MapReduce. So abstraction is important. Abstraction. So you have a basic idea, and then you have a lot of platform. You code still like you code for one computer system, but you need to have the concepts there when you code, how to utilize the services provided by that framework. Okay. Let's continue for the quiz time. So this is the end of this section. Okay, for this computer system architecture. Okay, so let's look at the three multiple choice questions: single, just choice, multiple choice, then multiple choice. But only one answer. Okay, one option is correct. So which of the following would lead you to believe that a given system is a SMP, so symmetric multiprocessing type system? Symmetric means what? A. Each processor is assigned a specific task. B. There's a both worker relationship between the processors. Similar like this one, like specific, and then each processor performs all tasks within the operating system. None of the above. Which one? So symmetric, correct? We mentioned symmetric, that means they can do everything. This is not true, correct? This is also not true, because both are the worker. So worker cannot do both job. Both will not do work job. None of above. No. C is correct, because each processor performs all tasks, okay, within the operating system. So the C is correct. So let's look at the second one. A cluster system gathered together multiple CPUs to accomplish computational work. B is an operating system that provides file sharing across a network. C is used when rigid time requirements are present. D can only operate one application at one time. So which one is correct? A cluster system, correct? This of course is wrong. It's used when rigid time, maybe not. Sometimes maybe we just want to store data. Is or if not so urgent, correct? Not so urgent, but we want to process it as quick as possible, because it's cluster system combines several systems together. Is a operating system? No. Computer class system contains not only operating system software, also contains hardware that provides file sharing. Not only file sharing, they can do computation as well. So A is correct. Gathers together multiple CPUs to accomplish computational work. If it's simple task, you don't need to use a cluster. Correct? Let's look at the last one. A dual core system. Dual core we mentioned requires each core has its own cache memory. True or false? Still remember, for that one they have L1 shared, but L2 not shared, correct? So it's false. This one, correct? They don't say they have own, because this is L1 is own, but L2 is shared, so we cannot say they have their own. Okay, so this is about a computer system architecture. Okay, let's continue for the next operating system operations. So once you have all the knowledge here, computer system, one computer maybe computing system, and then multiple computers, CPUs together. This is one, you can see it is one CPU system. This is the multiple CPU systems. Okay, once you have this knowledge, now we look at the operating system. What operating system can do for us, already mentioned there, but here we just give you more details. That means what type of things operating system will do. For example, when you have your computer there, you already install operating system, you power it on, and then what is going on? Which program is running first? And then when the operating system is ready, we don't do anything. What operating system will do? When we do something, we want to run some program, we want to perform some tasks, any specific thing will be done by operating system. Okay, so we'll talk about this. So here we first talk about when we power on a computer, what is the things going on? What is things going on there? So the first one, in fact, we have bootstrap program. So usually we will save this bootstrap program in a non-volatile storage, for example, flash memory or some hard disk and so on. Correct? Because this one must be always there. Once the power is there, and then we first load this bootstrap program into the memory. So this one is like the commander. This program will further load other kernel, that means the most necessary important part of operating system that will always be there or running. when your operating system is on. Okay, and then some others you can open, you can disable, you can end. Okay, for example, even we mentioned about operating system. Okay, you have some system programs like a calculator, calendar, like those things, even maybe Outlook. So this one is built on top of those. Maybe Outlook is maybe not a good example. It's like an application program, but like a calculator, like this shipped together with you. So that's called system programs. They build on operating system, but a lot of must. So you can decide whether you want to keep it running those things or end them. But kernel things you cannot end. If you end, they will maybe some surface will be not be able to for you to end those things. Some may be still okay. So that means Bootstrap will help to load the kernels, and after that we'll load some system daemons. This is surfaces provided outside of the kernel. That means it's not belonging to the kernel, but is some system daemon surface. Okay, surfaces. Just consider, for example, now I open this one. Okay? This is my task manager. I can know which daemon is running, like here. Okay, some are belonging to my applications. Some are belonging to this band, like the Windows, Windows part, the surface. So these are belonging to the daemons. That means they are always running there. It's provided as the surfaces. You may be able to end some of them. For example, you don't want to use some functionalities. You can end them without a serious problem, without affecting your usage. Okay, but for some, maybe you cannot do that. Otherwise, the system will be not available for usage. For example, like a Linux, here I'm using Windows 10. If it's Linux, the first system program to be run after you load the kernel will be the system D. Okay, and then this system D will load other daemons. So that means we first run this. We have Bootstrap program, and then we run this system D. System D will load other daemons. Okay, excuse me. And then the kernel will be kernel is like in the, for example, if we use inside the hardware, and this one is OS kernel. Okay. And then how can we interact with others? Maybe you have system programs, you have apps, you have system programs. So how can we interact with the system kernels? So we use the interrupt. I think we spent a lot of time in explaining this one in our last lecture. So interrupt, that means without interruption, I will do my own things. If there's an interrupt, I will just handle the interrupt accordingly. Of course, I need to look at the privileges, whether it's high priority or low priority. And then maybe there's a queue we are based on some mechanism to schedule the interrupt handling. And then hardware interrupt, software interrupt, we may have these two. Hardware interrupt, for example, you power on, power down, like this one, like these things. The power is gone. Of course, you need to do something. You can only shut down the tasks. Okay. And then if some interruption, you insert USB, another I/O, or plug out, like this hardware driven. Okay. Sometimes we also have software. For example, you are running a program, and then you use Java. You have exception. You have exception library. We call that package, that classes, and then the exception will be trapped by the operating system. and then they will stop your program. Okay, they will stop it. So this is called a software error, also called that means some interrupt, also called exception or trap. And then for this type, software type, there can be software error, for example, defeating by errors, okay, or overflow. Okay. And the request for operating system service, this is very common. For example, you use something to read the files. You need to read the files. You need to use the system calls. You print something, you output something. This will use the system calls. So if you have, you can find if you program, you have a loop. If you print out everything during one loop, you may have a significant delay in your running. The reason that you have to handle the interrupt every time when you do the input output. CPU will not do anything. They will just save your current state and then handle the interrupt. Let the devices finish and then notice the CPU, not the interrupt, has been handled, and then CPU can continue. Okay, we showed the example before. So all the system calls will cause software interrupt. And also some other process problem, including like infinite loop. Infinite loop processes modify each other or operating system. So for example, you want to put your program in an infinite loop, okay, infinite loop, that will cause some problem, correct? Or processes want to communicate each other, want to modify others' data, multiprocess data. This is also called interrupt, or even the operating system, the mode. Okay, we'll give some examples later. So this is about the process communication. This is about the process control. So like these things, all of these things will involve the software interrupt. So we use interrupt to interact with the kernel, to let the kernel finish the task. So here show the multi-programming. Okay, this is the second, maybe the previous one. We said the basic idea about operating systems. So next one we want to talk about is multi-programming. So that means operating system also has these functionalities, also have this operation. They can schedule your tasks, your jobs. Okay, we call it job scheduling. So let's look at, for example, we call this multi-programming. That means we have multiple programs running at the same time in the system. Each time we don't only run one task. The reason is that if you only run one task at one time, it will be a very wasting method to use the resource. Because sometimes, for example, you have a job, currently you are running, okay, and after a while you want to print. So during this print, you may just last for a while. Your CPU is idle, cannot do anything. Sometimes maybe you want to read the data again, read more data. So you are reading the data from disk. So the CPU is also not doing anything. CPU is idling. So you waste a lot for the critical resources like CPU, memory, and so on. So we want to have multiple programs running at the same time in the computer system. That's the idea. Okay. So multi-programming organizes jobs. Jobs contains code and the data together. So code, that's the instruction. Data, so that's the data you want to process. Okay. So we combine these two together. So we organize these two. So CPU always has one to execute. So that means you arrange multiple jobs loaded into the memory, make them ready to be scheduled by the CPU. And then once the CPU is available, for example, I'm doing the CPU first. After a while, I want to do loading more data or printing, so I don't use CPU. So the current CPU can schedule to run another job. Once I finish, maybe I need to queue again, and then I can get another running time. So this is like multiple tasks, multiple jobs. Usually here we use jobs for the tradition. Okay, multiple jobs. We share the same resources. Then you have a high efficiency in utilizing these things. Okay, and then a subset of total jobs in the system is kept in memory. So that means sometimes maybe we don't need to load all the jobs into the memory. The reason is that we may not be able to load all of them. This first one. Second one is that maybe no need, okay? Because instead there's a long queue there, so no need to queue inside. So you can queue outside. So that's the reason. And one job selected and run via the job scheduling. So this means we have a job scheduling program in our operating system. So it's a module in our operating system. This job scheduler will select one job to be run on CPU. Okay, because it's ready. Okay? So later we talk about the different states for a job. Okay? We later talk about it. That will be a process. Once you select a job, make it run on CPU, then it become a process. Give a new name. Job maybe things like our common name or most common, easy to understand name to assign to refer to a task to finish on a computer system. That's a job. When one job has to wait, for example, like I/O, we mentioned input output, load the data, output the result, print the results. So OS switches to another job. So that means this is the most, maybe one of the most important functionalities for our operating system. So that means multiple jobs can be scheduled at the same time. At the same time here means within the time range, we have this multiple jobs. Not only one job is in this system. We have multiple jobs which are running. Right? Sometimes running this one, sometimes running that one. But within this period of time, we have multiple jobs are running. Right? Multiple jobs running there. Okay. So one job cannot continue due to some other issues, other I/O or something, common issue maybe sometime. So we can schedule another job. Don't need to wait till the current job finish the I/O and then continue the rest. Okay. So this is multitasking. Okay, this is previously we call it multi-programming. That means we put multiple jobs in the system. And then here we set a multitasking. That means the running process, the running period for the tasks on the GPU. So we call it multitasking because the CPU is not designed to run only one task at one time. They can do multiple tasks at the same time. Okay. So in fact, this is also called a time sharing system. So why is it time sharing system? Because sometimes running for my jobs for some time, and then run your jobs for some time, and then run another person's job for some time. So multiple users can share the resources. Each of the user will be allocated some piece of time to be running, and then as long as it can give the users a sense of interactivity, you don't fear the CPU is shared by multiple users, because according to you, for example, once you are surf on a website, most of the time you don't do anything, right? You just reading, and then sometime occasionally will roll down or roll up, kind of click. So when you are doing like that, you don't need to use the CPU, right? You are looking at the screen, you are thinking. So in fact the CPU is idle there, so you can allow another user to share the resource. So this is the idea. As long as it make you feel okay, this is interactive, you feel satisfied, right? So this is a logical extension of the batch system. So the idea for batch system is that we run multiple tasks together, just queued in beforehand, and then during the same time we run multiple tasks there. Okay, so the CPU is, but this one is more interactive. The CPU, because that one is pre-ordered, okay? This one we do a dynamic scheduling. CPU will switch jobs so frequently that users can interact with each job while it's running. So the most important thing here is that CPU will just switch among the jobs very often, and each job will be get scheduled within very small amount of time. Even within a very small amount of time, your job will still be get scheduled and running for a while, and then next one for another job. So basically during this time you already get your results because CPU is quick, right? So you already meet your requirement, and then they can run some other user's job. So it will creative interactive computing. What it means interactive, as long as the response time is less than 1 second, so you don't need to wait. Okay? If it's more than 1 second, you think it's not interactive, okay? Not real time. Each user has at least one program executing in memory. So if one program means a job has code and data. If this job and data, this program, this task, this job has been loaded into the memory, and the data code has been loaded, maybe partially, but is ready to be scheduled, then we say this is a process, because this is the running state of the task or the job. If it is a static idea, for example, we save the job on the hard disk, not running, only the code is there. Okay, save the code and data is over there, but it's not running. That will be a job. But if it's ready to be scheduled by a CPU unit, we say processing unit can be a CPU core or CPU, then it will be a process, which call this one, give a new name, process. That's why you can find out we have chapter maybe 3. Chapter 3 maybe is still job. Is called chapter 3 is processes, and then we have scheduling. With chapter 5. Chapter 4 is threads and concurrency. Threads, even low level, and the process is high level. I mentioned process is highest level or higher level, and the thread is low level. One process can have multiple threads. A process is a scheduling unit, the smallest CPU scheduling unit, and the threads is the smallest running unit, means it can be run on one CPU core, and one CPU can schedule a process but it cannot schedule a thread, because you must run all the threads together at the same time for within one process. You cannot run or only one thread of process and then waiting for others. So that's not possible. So process is the smallest scheduling unit, and the thread is the smallest running unit. Okay, so that means it's ready, it's loaded into memory for the job. That will be the process. So current state is ready. Once it's scheduled by the CPU, and then it's running. That's called running. right? And then maybe during some time we cannot get scheduled, so we are running, we are doing I/O, and then once I/O is done, we need to put it into wait, right? Into wait to be scheduled next, and then maybe sometime we have to finish, segment finished, then that will be complete. And then during running maybe something error, and then we have some we need to do the just like block the running for the rest. And then we have maybe another one called something later we will consider about that one. Just like this, some exception we need to put it into another state to differentiate with the previous one. You finish the I/O and then go to wait. If several jobs ready to run at the same time, if multiple jobs are waiting there, so you need to have a strategy or algorithm to select a job to be run on the CPU. So you must make a decision. How to make a decision? So you have chapter 5, right? So that's the CPU scheduling. You can schedule the job according to, for example, what's the remaining running time, shortest one first, or what is the priority, the highest priority first, or you can just use a time frame. Each one only run time frame. So shortest first time first served, FCFS. So that's the CPU scheduler programs will do these things. Okay. If processes don't fit the memory, swapping moves them in and out to run. Don't fit here usually means either code or the data cannot be all loaded into the memory because they are too big, or existing memory is not enough to load all the data and the code, instruction code. So we use swapping. Swapping means something move out, something move in, right? Memory. So into a switch, swap. So page in and page out. If we use page-based memory segmentation system with page, and then if we use segment, okay. So that means here we want to load something in, load some out. We want to load something in, but there's no space. We must load something out. So unused data, unused code, we can load it out. Okay? If we want to use it again, we can load it again. So how to load something out? You need to have an algorithm. So this is memory management. For example, list unused memory page. Okay? List unused. For that means recently I haven't used this page for longest time. Maybe in the future I will also not use it in the longest time. So maybe the least chance to use that page, so I can load this one. Or you can just use some other methods. So we will learn this scheduling management as well. So this one tell you how to make it work. And then we can use a virtual memory. We mentioned it before, Kat. Virtual memory, you don't need to load all the data and the code into the memory, but it still can load can run a program which has larger space than the memory. The reason is that we allocate some space, some storage from the disk, and then temporarily state the data or code into the disk, and then we switch between the memory and the data disk region, but we still can run the program, because usually we have some characteristics for process. If you process data, you will always process the labeling data. You don't randomly jump on the back and forth. If we process code, we also process code labeling code. So that's why you just need to load a piece of data, a piece of code, a piece of data. You don't need to load all of them all together at the same time when the process is is ready to be scheduled. Okay, is initially loaded into memory. So you just do it in a dynamic way. So give you you don't fear this process. You think your memory is big enough to run this one. So even you have, for example, you have 1000 gigabytes data to process, but you only have 32 megabytes memory, but you still can run that program. Okay? You just doing it little by little. Okay? This is a very common idea for us to utilize resources. Okay? We can do like this way, just little by little. Okay, this is we can say it's the third task, third functionalities, or maybe the second functionalities. This one is introduction. This is multi-programming, multitasking. That means what operating system can do. They can do CPU scheduling. Okay, so here we look at this one. We give one example. For example, we can load multiple processes together with the operating system. Of course, need to be loaded into memory. Then it can run. So that's the idea. You can assemble multiple processes. Each process has some instruction and code, but not load all of them, and then allocate. So of course, this one may be based on some memory management systems, memory management algorithms. Okay. And then let's look at we mentioned about dual mode, okay, dual core before, but here we talk about the dual mode operation. So operating system can also do system calls, but how system calls will be run on the operating system, in the system, right? So in fact, we will differentiate two modes. When the program, for example, you have a program, now you are running, okay, where's my things here? This is your kernel, for example, is kernel, and then you have apps here. So sometimes you're running here, sometimes you need to use the kernel surface with an operating system calls. Then we want to differentiate the program's running mode, because for here is in your user mode. For here, in fact, is running the kernel node. For example, you want to do print, you want to do load the data, print the data, or output the result on the screen, like this. This is the kernel mode. This is the user mode. We differentiate these two, and then also we have hardware to code this one. Hardware, that means we save a bit. So we use mode bit to save this one. Mode bit provided by hardware. It will provide ability to distinguish whether the system is running on the user mode, or the kernel mode. That means whether this program currently is in the user's code or in the operating system code. If it's 1, that's user mode. If it's 0, that's kernel mode. Okay. So this is better, that is safer for us. So because if it's kernel mode, you may not be able to run something. If it's user mode, you can do whatever you can do. So this is the reason we want to differentiate. But we have a question. How can we guarantee that the user does not explicitly set the mode bit to kernel? Okay. So that means we will not allow user to change the current mode bit from 1 to 0 when it's running here. So this how can we how can we guarantee this? So the basic idea is that system call change mode to kernel. So we'll give one example. So that means, for example, you want to use a system call. So change mode to kernel, return from call, reset it to user. So the idea is that if we want to call the system call, when you enter this state, when the kernel mode, it will change to be kernel mode. And during this stage, you cannot do anything. Only after the kernel mode has the kernel mode program has finished, has been done. For example, putting something that has been done, you returned, and then you will change it to reset to user mode. So exactly like this one. So user process, okay, is running, and suddenly we want to do print in, out, like these things. And then the current mode bit is 1. So you have a trap. Trap means interruption, interrupt. So it will use interrupt to call the kernel surface system call. And then we change the bit to be 0. And then execute system call. That means we run that print or in output like these things. And then we finish, we change it back to user mode. So set it to be 1. And then return from the system call. Continue the rest if it's scheduled. Right? So this is the idea. That means we use this one to control, to control this one. Okay. But if you do this one, you change it to be kernel, you change that one, because that's not available for you, because it's hardware set. So it's only set by the operating system. You are not available to set that value. They will maintain this mechanism. So once you enter this kernel mode, we change it to be 0, and ready to be returned, change to be 1. And then you have low access to change this mode bit. That's the reason. Okay. And some instructions maybe need to be carefully processed. If like those things, because they may, if you this instruction, if you allow users to run those instructions, we may cause system errors. If like that one, we design those instructions to be privileged, can only run in kernel mode. That means user cannot run that code, because this one can only be run by kernel. That means only kernel can call it or execute it. Okay, there's some instructions which can do that. For example, format system, maybe just in for example. Okay, this is the idea. Okay, so next one we talk about in operating system, we also provide a mechanism called a timer. So this was the last service or functionality which can be operation which can be done by the operating system. Okay, timer. So basically, timer, that means we want to use a timer for a lot of cases. So here we give some examples. So the timer is just to prevent infinite loop. For example, some process due to the code bugs in the program, we may enter infinite loop. So how can we stop or prevent these things? Because if like this infinite loop, so no other task maybe can be scheduled. Okay, this one we call the process hogging resources. So you cannot if we don't detect these things, we don't stop it, and then it will always occupy the resources, and the other processes which are waiting for the resources cannot be get scheduled to continue. So timer is set to interrupt the computer after some time period. So after some time period, if you cannot continue, for example, like the deadlock detection, we may detect, okay, something going bad based on timer, and then we can stop, we can kill something, or we can put it to ready to be run again, but not running. Keep a counter that is decremented by the physical clock. So that means how can we implement the timer? The basic idea is that we can, you don't need to use time counting. You can just have a very large number, maybe some number, and every time you decrease it, you decrease this one, n by 1, n by 2, n by 3. You decrease the number by a period of time until it reaches 0, means the timer is out. Okay, time is on. Okay? That means time is due. Okay. So this is how we do the timer. It's like a stopwatch. Operating system set the counter. This is a prefinished instruction. That means the user cannot do that. When counted 0, we generate an interrupt. So that means interrupt this one cannot be continued. So interrupt the running of the process on the CPU. This one will be set up before scheduling process. That means for each process, we may set a timer for it to regain control or terminate program that exceeded allotted time. So that means we want to have control on the CPU scheduling, CPU resources. If some processes has exceeded its allocated time, we must terminate, or at least just put the process in the queue again. Just your time is due. It's very like, for example, we mentioned the time sharing system. Sometimes we also use, for example, each process is only scheduled to be run on the same amount of time. So we can use a timer to count the time. So do not exceed the time. Right? This one means we need to have a timer to control. Otherwise, you don't know when to interrupt the process. Sometimes you don't really stop the process, terminate. You just hang up it. Okay, we set what's the state? So that means just revoke, or just like you hang up this process running and put it into wait state. Okay, I think this is all the operating system operation. That means operating system can do such things. It can do, let's go for a little bit, and after that we have a quiz. This is the overall idea. That means what is the initial stage when operating system is on, and how user program interact with the kernel based on the system calls. And then we run multiple processes or jobs at the same time in the system via the multi-programming concepts. And then we also have multitasking, that CPU can be scheduled to run multiple tasks at the same time, during the same time period. Even we don't have enough memory, we can use a virtual memory using swapping, data swapping. And then we have talk about the dual mode of the operating system, running mode, kernel mode, how to handle this case, make sure it's safe, because it's hardware coded. So only in operating system, kernel can do the change. You don't have access to this one. And then third one, we also have a timer. Timer is to be used to control the running time, maximum running time on a CPU. And then we implement it based on decreasing a number. For example, based on how much time, and then you assign a number. This one also can be only controlled by operating system, so it's a prefinished instruction. Okay, let's look at the quiz, and then we release this part 3, this part first. Let's look at first question. ABCD can be used to prevent a user program from never returning control to the operating system. Portal, program counter, firewall, timer, okay, we just mentioned. What is another term for kernel mode? Supervisor mode, system mode, privilege mode, all of the above. In fact, we didn't mention, but in fact, all of the three are correct. So D is correct. Supervisor mode also kernel mode, and the privilege mode is also kernel mode. Same system mode is also kernel mode. The different names. What statement concerning privileged instruction is considered false? That means each of this one, which one is false related to privileged instruction. They may cause harm to the system. They can only be executed in kernel mode. They cannot be attempted from user mode. They are used to manage interrupts. So we mentioned, okay, we can use the privilege instruction to manage the interrupts. Okay, we just finished. And also we know they can only be executed in the kernel mode. That's what called the privilege instruction. We don't allow user to change. And they may cause harm to the system just because these instructions may cause harm to the system. So we give them more privilege. Okay? So it's privilege. So A, B, D, correct? So C is wrong. They cannot be attempted from user mode. In fact, they can, correct? They can be attempted from user mode. That's why we want to assign more higher privilege. Okay, that's the first part, and then we'll continue and then finish the second part for today's class. Okay.